And next we have Hans Lamecke from 1000 Shapes. Hello, Hans. Can you hear me?
I can hear you. Can you hear
Wonderful.
me?
Yes, I can. So I'm going to go ahead and let you get your presentation started. All right.
Can you see my screen? All right. You can see my screen, I hope.
Yes, our attendees are signaling a thumbs up. They see us.
Lots of thumbs up. Thank you, Kelsey, for the introduction, and thank you very much to Jan from Simq for the invitation to join this really wonderful and inspiring meeting. We had a lot of great presentations today, and yeah, it's also impressive what you do at Simq and what you have achieved over time. So congratulations. So yeah, my name is Hans Lamecke. I'm Managing Director at 1000 Shapes. Today, I would like to talk to you about correlating foreign function, predicting hemodynamics with machine learning. So maybe about first to introduce myself and my company, so you know who is talking to you today. 1000 Shapes. At 1000 Shapes, what is our vision is to improve the quality of life of people by enabling everyone to obtain or rely on optimally fitting products. So the focus of our work is really on geometry of things, especially of anatomy. And how do we do this? So we are a software company. So together with our customers and with our partners like Simq, for instance, we develop digital solutions with which fit optimized products, mainly in our case, medical products or therapies, can be realized technically and economically. Very important, especially in the medical sector, and in a way that the user experience is taken to a new level. That's what we are doing in a nutshell. So what we are offering is three main things. One is very basic, offer 3 anatomical models. So we create 3D models for you from available sensor data, CT, MRI, ultrasound, whatever, and all kinds of formats for you to use it readily in your workflows for your purposes, whatever that is. We also offer population analysis services, so very similar to what you've seen earlier by Materialized, the cohort analysis. What we do with these models for you is to reconstruct, for instance, physiological situations from pathologies. So if you have a pathological situation with these population models that we generate, we can kind of estimate what was the physiological situation, which then can serve as a template, as a guideline for reconstruction, for therapy planning, for instance. We also provide essential insight for better product design, very similar to what was shown earlier by Materialized. So if you have an insight into the population, you can design standard devices much more efficient. That's where we are helping. And finally, what we also do is custom workflow software. So we don't have a standard software solution. We offer to customize the workflows for your purposes. We are not really bound to a specific medical field. We do that from head to toe. But our mission here is to integrate the training or planning, design, or manufacturing tasks into really easy to use non-export software. So you don't need to be a CAD/CAM expert designer to use that software and achieve really fast workflows. That's how we think that we can only automate, especially individualized device creation or selection tasks. So that's the presence. What I would like to talk to you about today in this meeting is more about some future ideas that we are pursuing. So if you want to talk to us about what we're doing right now, you can always contact us via email or get contact from our Simq partners. So in a research project that we have done with some partners from Charité, so the Institute of Cardiovascular Assisted Medicine, as well as the German Heart Center, and Siemens Healthineers, we have worked on a project where we have created a system to predict hemodynamics for individualized treatment in real time. So let me show you in a very short video what's the vision behind that, what the system can achieve. So I hope this is running now. Yeah. So, okay, you load the individual data. We've seen that many times today before, MRI data, and you can inspect the geometry of the aortic arch in this case. And here the idea is that as a user, you can define a stenosis for this patient, and you see immediately what is the functional behavior of the system. So in this case, for instance, the pressure drop around the stenosis. And then you could do kind of virtual stenting, where you select how you would kind of treat this stenosis with what kind of stent, let's say, and in real time get a feedback about important values like a pressure drop, wall shear stress for that specific kind of treatment in real time. And that is kind of looks kind of magic. So you can do the same thing, not for stenosis, but also for aortic valve replacement, as shown in this case. So that's kind of the idea of this planning system. So how can this work in real time, especially for colleagues that are working on computational fluid dynamics? It's kind of magic how this can work. Yeah. So because computational fluid dynamics is computational expensive task to do. Yeah. So I will explain to you very, very high level how we have achieved this. And if you have further questions, of course, you can come back to us anytime. First of all, we are creating a shape database of representative shapes for such treatment plannings. Yeah? Not just shape, in fact, also boundary conditions for the flow. Based on that, we carefully selected these representative cases, run real CFD simulations, 5 hours per case, roughly. Okay. Now, what we have done here in order to make this real time, based on this input and output, so the shapes, the boundary conditions, representative cases, and the computational fluid dynamics results, we train a neural network. In this case, it's a recurrent neural network. And with this network, if we train this, then the kind of computation time for an individualized simulation, like trained or learned simulation, is just a fraction of a second. And that's what we mean by real time then. And how does this work? So there are two main ideas. One is that how you encode the shape for this purpose of training such hemodynamic parameter estimations with a point cloud model and a centerline model on which we encode the values that we want to learn and to train, like pressure, wall shear stress, and things like this. That's one idea. And then based on that, we use a bidirectional long short-term memory network, which is a specific neural network, if you like, to train the values on that shape encoding. So you can, if you want to understand more about how we're doing this, it's all documented and published, and you can look that up. I'll show you where you can find more information. So we also evaluated very carefully how accurate this prediction is. Of course, it's from our studies, it's not a perfect fit yet, but we see on this limited set of data where we've trained the model on that the overall trend is already produces quite a good accuracy and prediction of the results that we would get from reference ground truth CFD simulations. So for more details about this, you can go to this website of our consortium, where we have more information, publications for you to follow up on that. And yeah, that's my contribution for this conference today. Thank you very much for the attention. If you have any questions, feel free to contact myself, our company, or your partners at Simq, and we can get into discussion. Looking forward to that. Thank you very much.
Thank you, Hans, so much. All right, I see some applause here.
Hands are growing. Thank you.
Wonderful. Okay, so like Hans said, he left a lot of information on where to reach them, We also, like we said, record the presentation, so you can go ahead and rewatch that, and he can help you answer any other questions afterwards. Also, I encourage everyone, like I have been, stay behind and join the lobby expo area, and we can interact and network there. Alrighty, Hans, thank you so much.
Thank you, Kelsey. Bye-bye.
Bye-bye.